Hello and welcome to Simulation TV. My name's Shawn Gedman, and today I'd like to go over simulation in action, simulation Moldflow, packing analysis overview. So our problem description for what we're going to go through today is basically an exercise. We'll look how to use a pack analysis to help us determine a pack profile for our plastic tractor here. So some key learning objectives that we'll go over will be to how to set up a packing analysis first of all, how to determine gate freeze once you have your pack results, and then some pack profile considerations and tips to help you get started with optimizing your profile here. All right, so at this point we have our hood to a tractor that we have here, a little plastic tractor toy. We're going to focus on the hood section for this exercise, and we're going to go through the setting up a packing analysis at this point. So the second study here, I've isolated the tractor hood. I've put a simple sprue and gate system on it. Maybe not something we typically use for this particular design, but just to keep it simple for the exercise, we'll focus on this particular design here. So the first thing we want to do, of course, we already have our gate location analysis that we ran by this time, hopefully our molding window analysis that we've also run at this point, and that's given us a good choice on our gate location. We've also have kind of a rough idea on what our fill time will be, our mold melt temps, and from there we're going to go in our pack analysis. So we'll come down here, select our analysis sequence. It's going to be a fill pack analysis here, because you have to have your fill, of course, that leads into your pack. Now we have our material selected, our feed system, our ejection location, everything in there. So we're going to go to our process settings now. And as I mentioned, we ran our molding window analysis by now, hopefully to get a good idea on the material and the good mold surface temp, melt temp, fill time. So I have all these in here from those previous analyses, hopefully. Now, the other things we'll have to take a look at are VP switchover. This is basically when you're going to switch from filling control, a velocity control, to a pressure control. And typically we go, I see normally a 98 to 99%, but there are certainly circumstances this might not be the case. As for our pack profile, just to start with, we're going to go with the defaults. The defaults are a good starting point for us. It's going to be a 10-second pack profile with 80% of the max fill pressure. And then cooling time is another thing that we'll specify here. Typically we leave this a little long just so we can see our gate freeze. So 20 seconds for this part is going to be plenty of time for us to see gate freeze. It should freeze well within that time frame. From this point, we would just start analyses. I have it completed at this point to save us some time, and then we would get into our results. So when you're looking at results for the pack analysis, we want to look at a few key results. One of them being your pressure. So we look at our pressure plots here, and you could do this in an XY plot, you could do it in the shaded plot. And what this is going to tell us two different things. One, we want to take a look at our peak pressure here, which is 79.23 megapascals at this point. And we want to just make sure that that's within our machine limitations. General guideline, you don't want to be more than 80% of your capacity on this. You can also find this information in your logs as well. It's typically going to be right at your VP switchover, your max pressure, which is what we're seeing here. So considering that's okay, we can move on, maybe check our clamp force predictions and see if that is also within, say, 80% of our machine capacity. And then we know it's a good fit for our machine. And I mentioned there's a second thing we can look at with this pressure plot as well, and that's typically uniformity. you look at some uniformity of pressure distribution over your part, and that'll give you kind of a good indication of what some of your shrinkage values are going to be. And because pressure leads to shrinkage, and you can either help reduce it or increase it depending on higher or lower pressures and variation within your part. So that leads us into probably the most important portion of the pack analysis that most of us will be interested in, and that's going to be our volumetric shrinkage plot. So I'll go to our volumetric shrinkage. And what this is going to show us is essentially how much the part's going to shrink. It's going to take the volume of the part based off your tool dimension and do a comparison for when that part reaches room temperature at 25 degrees Celsius. So this is going to give us a good indication of whether our part's packed out adequately enough, if we're going to maybe have some issues with deflection, warpage problems in the future. Now, some things we'll look at is distribution. This is all going to depend on what type of material you're using. Some materials are just higher shrink materials than others, so some you may see in the 6 to 7% range and not think anything of it. Others you might want to see more in the 4 or 5 or lower. So that's one thing you want to keep in mind there, that it's kind of not a one shoe fits all here. You need to have some idea what your material's shrinkage characteristics are, how they're going to behave. But you can see distribution and kind of uniformity, I guess we could say, is key in these situations, because when you have differential shrinkage or shrinkage that varies greatly from region to region in your part, that's when you kind of get into trouble with your deflection. Aside from that, we'll go into a little later some tips or tricks that you could use in your pack profile to tweak, let's say, your pack profile, your volumetric shrinkage, and help you with your deflection here. The third and final plot that we're looking at, of course, in here is also going to be frozen layer fraction. This is going to help us with gate freeze, or determining when our gate freezes. And this is great for, of course, making sure that we're not closing the gate prior to it freezing and having undesirable part quality. It'll also help us with minimizing our cycle. We could easily say, well, let's leave it 20 seconds, but that's not good for our cycle time. So that's where frozen layer fraction comes in. Now with frozen layer fraction, we're just going to go in. I typically go into the properties and turn off nodal averaging. It's not going to be as pretty of a picture, but it's going to give you a little more accurate of a read on your gate region. So we have nodal averaging off, and then basically we just step through our analyses until we turn red, which is 1, meaning that section is completely frozen 100%. In this case, it's about 6 seconds. So at this point, I could go into my pack profile, optimize my cycle possibly by cutting it down. Right now it's 10 seconds with a 20-second cool. We can put this down to, say, maybe 7 seconds, optimize our cycle and our cool later, and save some time. All right, at this point, we'll go into another portion where I'm going to show you some tricks with your pack profile that you can use to tweak your volumetric shrinkage and some issues you might have with determining your appropriate pack profile. All right, so there are 3 areas that we're kind of going to focus on for our pack profile and the tips that we're going to cover. So we'll break them up into the end region, which is more towards the end of fill, last place to fill, the gate region, which of course is going to be around your gate, and then your mid region, which will be between the two and the part. So just some little tricks that we can do, or that I've been taught this years and years ago about, how we might be able to address shrinkage in these particular areas. So if you're having a problem with the end region, or you need to adjust something there, what we can do is shorten our pressure duration, and that will of course raise our volumetric shrinkage, or we can lengthen it out, increase the time, and that'll help lower it. And you might ask, why would I want to raise volumetric shrinkage? Well, again, uniformity is kind of the key here. So, raising shrinkage might not always be great if you're considering or having an issue with a critical dimension that you need to hit, but this will help with deflection. If we can get a uniform volumetric shrinkage, our deflection should be reduced, and you'll never get rid of warpage altogether, but we can do our best to make it meet our tolerances. So this is one way we can do that in the end region. Focusing on the gate region, we have what's called a decay, which is when your pressure, it will be at a constant rate typically, and then you'll ramp down. Now you can have multiple steps in this profile. You could set this up however you wish, but again, we're going to keep it simple for this exercise. And in this case, if you would have a slower decay, of course your volumetric shrinkage would be a little lower in the gate region. If you had a faster decay, then it would be a little higher. Now our final tip here is going to be the mid region. To focus on that, you can put what we call a knee, or you could put a step or a knee in this curve. So if you put a knee that increases, then you can have lower volumetric shrinkage in the mid regions. If you decrease it, or kind of have an inverted knee there, then what you'll have is some raised volumetric shrinkage in the mid region of the part. Of course, these are just some very basic tips. You can play around with these. As I said, I've played with these over many years. This is kind of what I was taught in my training and learning Moldflow along the years, and it's worked well for me. So I just wanted to pass these on to you in an effort to help you optimize your pack profile. And that's all I have for today, and thank you for coming.